This video is for Physics of the Universe, Unit 1.5, Conservation of Momentum. Today's essential question is, how does the law of conservation of momentum help us understand collisions, motion, and safety in the real world? Hello, baby birds. Today we're exploring one of physics' most powerful conservation laws, the law of conservation of momentum. Momentum explains how motion is transferred whenever two objects collide, from car crashes to football tackles to rockets moving through space. By the end of this lecture, you'll understand how momentum is shared, how it's conserved, and how engineers and scientists use this principle to make the world safer and more efficient. Imagine you're riding in a friend's car with your feet up on the dashboard. If the airbag deploys at nearly 200 miles per hour, the force on your legs would be enormous. Airbags protect passengers by spreading momentum change over time, which reduces force. This example shows how understanding momentum isn't just theory, it's a matter of safety. So in this video, we'll connect real-world situations like this to the physics that governs every collision. Remember, our essential question is about momentum. How can it be transferred during a collision, for example, in a car crash? Keep this in mind as we move through the rest of the video. We'll look at what momentum is, how it behaves in collisions, and why total momentum stays the same, even when individual objects slow down, stop, or change direction. Think about this. Which is harder to stop? A small car or a large tractor-trailer moving at that same speed? The truck is going to be harder to stop because it has more momentum, a quantity that depends on both mass and velocity. Momentum tells us how difficult it is to change an object's motion. This sets up our exploration of what momentum really means and how it's calculated. Momentum is defined by the equation P is equal to m multiplied by v. This means that an object's momentum increases if its mass or its velocity increases. Momentum is a vector quantity, which means it has both magnitude and direction. The units for momentum are kilogram meters per second, or kg m over s. So, doubling a car's mass, or doubling its speed, both double its momentum. But reversing direction flips its sign. This directional property will be crucial when we start solving problems. Momentum and kinetic energy both describe motion, but they aren't the same. Momentum is a vector, while kinetic energy is a scalar. Momentum depends linearly on velocity, while kinetic energy depends on velocity squared. This means a car going twice as fast has twice the momentum, but that same car going twice as fast has 4 times the kinetic energy. Both quantities help us analyze motion, but the momentum focuses on the transfer of motion and force during interactions. The law of conservation of momentum states that in a closed system, meaning one without external forces, the total momentum before a collision equals the total momentum after the collision. This is why colliding billiard balls, atoms in gas, or even spacecraft all obey the same rule. Momentum may move from one object to another, but the total system momentum remains unchanged. So let's visualize this process. Before the collision, each object has its own velocity and momentum. During the collision, forces act between the objects, transferring momentum. After the collision, the total momentum of the system stays constant, even though the individual speeds have changed. Mathematically, it's written as Pi is equal to Pf, meaning initial momentum equals final momentum. Now we'll apply this idea to a simple example. A cue ball with a mass of 0.17 kilograms strikes an 8 ball with a mass of 0.16 kilograms at 7.6 meters per second. After the collision, the cue ball stops completely. Our goal in this sample is to find the 8 ball's final velocity using the conservation law. So step 1, list the known values. The cue ball has a mass of 0.17 kilograms. The 8 ball has a mass of 0.16 kilograms. The cue ball has an initial velocity of 7.6 meters per second, while the 8 ball has an initial velocity of 0 meters per second. Step 2, set initial momentum equal to the final momentum. After the collision, the cue ball's velocity is 0. So 1.3 is equal to 0.16 times final velocity. So then we can divide, giving us a final velocity of 8.1 meters per second. The 8 ball moves forward at 8.1 meters per second in the same direction. No momentum vanished, it was transferred. Collisions come in 2 types. Elastic collisions conserve both momentum and kinetic energy, like 2 steel bearings bouncing apart. Inelastic collisions still conserve momentum, but some kinetic energy changes into sound, heat, or deformation. Car crashes are elastic because energy is absorbed by the crumpling metal and the friction of the collision. Here, on the left, we see elastic collisions, right? We see the balls separate cleanly and nearly equal speeds in opposite directions. On the right-hand side, we see inelastic collisions because we're showing the objects sticking together and moving as one. This is a key difference between elastic collisions and inelastic collisions. Also, even though kinetic energy decreases in the inelastic collision, total momentum is still conserved. Now let's test this with a real-world example. A 95 kilogram offensive player runs to the right at 6 meters per second, and a 120 kilogram defensive player runs towards the left at 2 meters per second. They collide and move together. This is a perfectly inelastic collision, so let's find their final velocity. So first, we'll define moving to the right as positive. We'll define moving to the left as negative. Next up, we'll calculate the initial momentum. The initial momentum is equal to the sum of the momentums of each of the objects involved. In this case, a 95 kilogram player moving at 6 meters per second to the right, so it has a positive sign, and a 120 kilogram player moving to the left at 2 meters per second, so that is a negative sign. Once we sum those quantities, we have an initial momentum of 330 kilogram meters per second. Next up, we'll apply the law of conservation of momentum. We know that at 330 is going to be equal to the combined mass of the 2 players because they now move as one. So we'll add the 95, the 120 kilograms. But because they're moving at the same velocity, their final velocities will be the same, allowing us to factor out final velocity from both terms. This allows us to set an equation that looks like 330 is equal to 215 multiplied by the final velocity. Using our simple algebra skills, we'll divide both sides by 215 to give us a final velocity of 1.5 meters per second. Now that is a positive value, so that indicates that 1.5 meters per second is to the right. Now let's calculate the kinetic energy loss. Before the impact, the offensive player's kinetic energy is about 1,700 joules. After the contact, it's only about 110 joules. The difference between those two values, again nearly 1600 joules, turns into heat, sound, and deformation. This illustrates that inelastic collisions keep momentum but lose kinetic energy. Newton's cradle demonstrates both momentum and energy transfer. When one sphere hits the line, only the sphere at the opposite end swings away. Because all spheres have equal mass, the momentum passes straight through. This is nearly a perfectly elastic interaction, ideal for showing conservation visually. In a closed system, total momentum before equals total momentum after, like hockey pucks sliding on a frictionless ice surface. In an open system, external forces change momentum, like a car braking or a rocket thrusting. Identifying whether a system is open or closed is the first step in any momentum analysis. Conservation holds only when no external forces act. So in an open system, outside influences like friction or air resistance apply a net force that changes the overall momentum. According to Newton's second law, which is F is equal to ma, we can substitute net force is equal to the change in momentum divided by the change in time. So whenever there is a net force, momentum changes over time. Airbags and seatbelts don't reduce the momentum change during a crash, they increase the time it takes for that change to occur. Again, since net force is equal to the change in momentum divided by the change in time, a longer collision means a smaller force. That's why crumple zones, padding, and airbags save lives. They stretch the momentum transfer over a longer time period. The conservation of momentum shows up everywhere. Sports, we see pitchers, golfers, and boxers using body mass to maximize momentum transfer. In space, we see rockets move forward by expelling exhaust backward. In engineering, we see designers create barriers and materials that absorb momentum safely. These examples prove this law governs everything from recreation to technology. Now, when you solve momentum problems, use this 5-step method. First, identify the system and confirm that it's closed. Number 2, list masses and velocities with their directions. 3, calculate initial momentum. 4, calculate final momentum. And 5, set them equal to one another and then solve for the term the question is asking for. Remember, always include direction. That is what makes momentum a vector quantity. So let's work through this practice problem. A 0.11 kilogram puck moving 2.2 meters per second hits a 0.42 kilogram bottle that's at rest. Afterward, the bottle slides 0.84 meters per second forward. Find the puck's final velocity using the conservation law. So let's start by setting up our equation. We know that initial momentum is equal to final momentum, and each momentum is equal to m times v. So we can set up our equation as we see on the screen here. 0.11 times 2.2 is going to be equal to 0.11 times the velocity of the puck plus the 0.42 times 0.84. Once we have set these two things equal together, we can use our simple algebra skills to solve for the velocity of the puck. Once we add like terms, we see that 0.242 is equal to 0.11 multiplied by the velocity of the puck plus 0.353. Once we solve for the final velocity of the puck, we see that it ends up being 1.0 meters per second. And this means that the puck moves forward more slowly because of its momentum being transferred into the bottle, which makes sense using your common sense. So let's summarize. First, momentum is equal to mass times velocity, which has the units of kilograms meters per second. Secondly, total momentum in a closed system is conserved. Thirdly, elastic collisions keep kinetic energy. Inelastic collisions do not. Fourthly, external forces change momentum via impulse. Change in momentum divided by change in time. So, how can momentum be transferred during a car collision? The total system momentum stays constant. It's simply shared among the objects in the collision. Safety features lengthen the collision time, which reduces forces and prevents injury. Now, that is conservation of momentum in action, a principle connecting everyday experiences to universal physical laws. At this point, you should be able to generate a full and appropriate response to today's essential question. How does the law of conservation of momentum help us understand collisions, motions, and safety in the real world?